Hi, I'm finishing my 5th year at Georgia Tech and wanted to make a video on my perspective of data science, what I wish I would have heard starting my education, and how I view the bigger picture. This video, I'll just go over like the general concepts. I only expect you to know algebra, derivatives, and integrals. And for experienced data scientists and other videos, they often focus on specific problems and models without thinking about the concepts or jumping straight to Python. If you are an experienced data scientist, hopefully this video will help you relate concepts and brainstorm problems and models. The most important aspect of a data scientist is viewing a situation and formulating it into a problem, and then formulating it into a model, and then actually coming up with the solution for that model is difficult. So yes, like with introducing what data science is, I would start with what is an optimization problem, and that is maximizing or minimizing a function, right? So we could do max f of x over x or min f of x over x. And so x is the variable that is changing, and f of x is the objective function, the function, or rather transformation that's doesn't have to be a function of the variable that is being maximized or minimized. And we can denote the x that produces this smallest or largest value as x star, and that's called the optimal solution. And then f of x star is going to be the optimal objective value, the largest or smallest possible value, optimal value or optimal objective value, right? And so in notation, when we write min over x of f of x, that's going to equal f of x star, or we could say f star. The actual value that the function has at its lowest point is called the minimum. Our x star is called the argument that minimizes the function. And it's often more important than what the objective is what the optimal solution is. And let's go through like a very simple example. If we were minimizing f of x equals x squared over x, right? So with just our single variable x and objective f, we can visualize it pretty easily because it's just x squared, right? So our minimum is going to be this vertex at 0, 0. So the function value is 0 at its lowest, right? To prove that, we would take the first derivative of x squared, which is 2x, right? And then set that equal to 0 to find our extreme point, the x star. And then to show that this is a global minimum, we would need the second derivative, which is 2, and so that's greater than 0 for all x. So this means we have a convex function, and when we have optimization over a convex function, that's when we're very likely to get a single optimal solution that is like truly better than every other value. If we look at a slightly more complicated example, still pretty simple, minimum ax plus b over x, right? So now our f of x, our objective is a linear function of x. X is still our variable, and a and b are called parameters. They're numbers that before we can solve this problem, we need to choose values for a and b. They could be 1 and 5 or 10 and 2 or whatever. But they're defining the problem and defining the specific scenario and model, etc. It means that the parameters are being chosen. And then we can write st for subject to, or such that x greater than or equal to 0. And so this is an example of a constraint. We're saying that we're finding the minimum value of this function only considering the inputs that are greater than 0, right? And then we could also have another constraint like x square root of x less than or equal to c. And then we can graph the feasible region, or the possible values for x that we're considering, right? It's just x going from 0 to c squared, because this is equivalent to saying x is less than c squared. And so those are the values of x that we're looking at, those between 0 and c squared, right? And so we can look at specific scenarios for the parameters, like if a was greater than 0 and b equals 0, what would our graph of f look like? It would look something like this, right? We'd have f as a line, and then the x-axis is there, and our minimum, so we have x greater than or equal to 0. So here we have x equals 0, right? So we're only considering the x on this side, and they also have to be less than x equals c squared. So we're considering these values of x. Which one has the smallest value of f? Well, that's going to be x equals 0. If we had a slope going the other way, then a negative slope, then our minimum would be c squared. Right, so in this scenario, we have x star equals 0, or generally, when we have a equals 0, we have x star equals 0, and a less than 0, x star equals c squared. B is in our objective, but it doesn't, changing the value of b doesn't change the optimal solution, right? It changes the f of x star, because you're just adding b to it, but that b is a constant being added the same at every x unchanging. Yeah, so really not every parameter is always super relevant. Let's look at a slightly bigger example of a linear objective. Minimum over x of f of x equals a1 x1 plus a2 x2 plus b. And now we have 3 parameters in our objective and 2 variables, right? X equals x1, x2 are the variables, and then a1, a2, and b are parameters. And we can add constraints to this problem. X greater than or equal to 0, so that's the same as saying x1 greater than 0 and x2 is greater than 0. And then we could relate the two of them with inequality like this, right? So let's try. Last time we were able to, on a 2D graph x and f of x. Now we have x1, x2, and f of x, so it would be like a 3-dimensional graph. But really, it's just more helpful to graph the feasible region, which x we're finding the maximum over. So let's go ahead and do that, right? So we have x1, x2, and we have x is greater than 0. So we're in the first quadrant. Both of those have to be positive. And then we have 2x1 is less than x2. So we can do x2 equals 2x1. That's the line. And then which side of the line is feasible? Well, we want x2 to be greater than 2x1. So it's this, yeah. Maybe to make it a little easier visually, let's switch the sign. So now we're talking about this region. And this goes on for forever. It's unbounded feasible region. So if a1 greater than 0 and a2 are greater than 0, again, we would have our solution is x star is 0, 0. When we have 2 positive coefficients, they're going to be minimized at 0. But if we had them both negative, right, then we would be incentivized to make x1 as large as possible and x2 as large as possible. It would be unbounded. So our feasible region is unbounded, but sometimes we still have um, a single optimal solution. Sometimes it's unbounded. Now we can convert this into a bounded region by adding a third constraint, right? So um, our constraints could be x greater than 0, 2x1 less greater than x2, and then we could have x1 less than or equal to c, right? Those would be our three constraints that we write in the such that, right? And we'll keep the same objective function. So basically, I'm just adding a straight line to make our region bounded. So x1 equals c is this line, and now we have to be um, less than that line. So this blue region is now our feasible region, and it's clearly bounded. And we can talk about now how do we find the optimal value. Well, we look at the boundary points. We have 0, 0, and then we have c is our x1, and our x2 value would be 2c, since this is the line 2x1 equals x2, right? And then here we would have c comma 0, since we're on the x1 axis. And since this is a linear region, we only need to evaluate the boundary points, and one of those at least will be the optimal solution. Again, if we had a1 greater than 0, a2 greater than 0, we would be incentivized to make both of them as small as possible. So we would want 0, 0 as our solution, right? And again, if they were both negative, we would want them both to be as large as possible. And so now that's this point. It doesn't go up to infinity, infinity. It stops at c to c, our feasible region, right? So x star equals c to c. And then if we had a1 less than 0 and a2 less than 0. Oh, wait. A2 greater than 0. Let's do that one next. Right, so now we want to make A2 as small as possible and x1 as large as possible. Right, we want to have a large x1, small x2. So our x star is going to be that C0 point. And then in this fourth case where we have A1 greater than 0, A2 less than 0, there's a couple things that could happen, right? It's we don't know whether A1 or A2 is larger. Sometimes we could end up with 0, 0 as the only optimal. Sometimes we could end up with C0 as the only optimal. But like if we looked, for example, at when A1 is equal to 0 and A2 is greater than 0, right? Then we would have our objective, we would have to compare the objective values at the three points, right? So like all of those, I was choosing x star by comparing f of 0, 0, f of c0, and f of c2c, and deciding which one has that largest objective value, then it's the optimal solution. Here, the x1 coefficient in the objective is 0, right? So our objective function is just going to be a2 times x2 plus b. And this is positive, so we want to make x2 as small as possible. So f of 0, 0 and f of c0 both have x2 as 0, so that their function value is just going to be b, right? And that's going to be the optimal objective value, right? So now our x star is the is 0, 0, and C0 are optimal, but also all of these other points on this line segment are optimal. Um, right? If we had C over 2 comma 0, we would still get B as our objective value. So X star is this line segment. We could write it as like um, x1 comma 0 for x1 goes between 0 and C, right? And so this is a special case of optimization problem. We have a linear objective and all our constraints are linear. All these constraints are linear functions. We don't have any quadratics or exponentials, etc. And so that is called a linear program. And that's why we're guaranteed to have X star the optimal solution on the boundary. For hundreds of variables and dozens of constraints, we can still evaluate the boundary points. Um, and we can do it sequentially, algorithmically, for the many different vertices of the boundary of the feasible region, right? And so that's called simplex algorithm. One of the fundamental ways of getting a solution to an optimization problem. After optimization problem, I would talk about models. And I split this into two types of models, data model and decision model. So a data model is when we're estimating the value of parameters from a data set. So we have a known data set. Let's say, for example, x, y are our data points, right? We have x values and y values. And then let's say the y values are something like this. Right? And then we could also think about implicitly, we have a column for the index I, 1, 2, 3, 4. So we have 4 data points. And we're saying based on this data set, we want to estimate parameters of some data model. So y hat equals f of x is going to be our model, right? We're saying that given an x value, we want to be able to predict the y value, right? So y hat is our predicted y value um, given an input x. And one common way to do this is linear regression. In linear regression, we have just a linear data model. So we're predicting y hat I as a linear function of xi. Right? So that means if you choose an x, then you can get the predicted value for y. Like let's say we wanted to extrapolate to x equals 5. What would our predicted y be? That would be y hat plugging in x equals 5. But now we want to ask how to choose a and b. That's where the data model comes in. We have to have an estimation technique, which is like how we choose the objective function. And in linear regression, that's least squares. So in least squares, we're trying to minimize the sum of squared error, right? So we want to choose the model that has the least squared error on this data set. And so we could write that as the minimum of the sum from points 1 to 4 of yi minus y hat I squared. So squared error is just the difference between the prediction and the actual value, and then squaring it. And so let's think about our example data set again. We have x and y. Let's graph the points. Something like this. And then what would be the optimal model? Well, we're going to be choosing specific values for a and b. So let's say that the optimal AB that we're estimating are a hat and b hat. right? And so then these are going to be the AB that minimize our objective function. So they're the arguments that minimize I equals 1 to 4 of yi minus the predicted y. So we can substitute in our linear model to get it in terms of a and b, right? So this minimization is a little complicated, but not that complicated. Um, but like it's like would you would watch another video about linear regression in order to understand it, right? But I'll just tell you for these data points, the solution would be having the line go from these 2 points, and this line would be y hat equals 2x plus 0. So our estimate for A is 2, and our estimate for B is 0. The other type of model is decision model. That's where we're choosing the value of a decision variable given known parameters, values, right? So both of these are optimization problems, data models and decision models. We're simply changing the meaning of the letters, the variables to fit example tasks. So let's say our decision variable is x. So we want to find the x star, the optimal x, by doing this. So our model would be to minimize over x, y equals ax plus b. So we want to choose the x that minimizes this function, and then we can add in a constraint. 0 less than or equal to x less than or equal to 10. Both data model or decision models could have constraints or no constraints. When we phrase it as a decision model, it's very likely we're going to have a constraint. And a lot of the time we have our variables are non-negative. But basically, A, B are no longer the parameters to be estimated. They're known parameters. And the x is the decision variable that is being changed. Right? We don't have a data set of known x values. But if we have a value and a b value, for example, this, we know what the optimal x is by solving this optimization problem. This problem would be pretty easy. Like as we've talked about before, since it's linear, we have this negative coefficient for x. We want to make x as large as possible within these bounds, right? So our x star is going to be 10, and our y star is when we plug x into the objective. Negative 2 times 10 plus 100 equals 80. We could use a data set to estimate parameters in a data model and then pass those parameters to a decision model to choose the value of decision variables, right? So in the layers, it's like data collection, then data model, then decision model. For example, like you could be collecting data on different store conditions, prices, possibly, and how much was sold, like price and quantity sold, and then form a data model relating those two, and then write a decision model choosing what your optimal price would be. What price would maximize the quantity sold, or rather, if your objective should be quantity sold times price for profit. Yeah. And now let's talk about types of variables. We talked about types of problems, models. Now let's talk about variables. Before, we had 0 less than or equal to x less than or equal to 10, right? And so visualizing the feasible region, the range of possible x, the set of possible values, it's 0 to 10. And so we could have x equals 1.21372 dot dot dot, or we could have x equals 2.000 dot dot dot. There's infinitely many values between 0 and 10 that x could take. right? So we call this a continuous variable because like the range of the variable is continuous and it's bounded. As we were talking about before, um, it it has to be between 0 and 10. Negative infinity and infinity are not possible. The other main type of variable is discrete, right? So let's say instead of having all the values between 0 and 10 possible, we'll say that the only possible values are the integers between 0 and 10. 0, 1, 2, 3, 4, etc., all the way to 10. And so now we only have 11 possible values instead of infinitely many possible values. So like x star equals 1.5 doesn't make any sense because 1.5 is not possible, but versus over here, 1.5 is very possible. And we can also have unbounded, like in the continuous case, that's pretty simple, right? We would say x is between 0 and infinity. So it's just any positive value. We could write x as being any positive integer as well, an unbounded discrete variable. So we could have 100 billion and 1, but not 100 billion and 1.5. We can't have any decimal places, but there are still an infinite number of values. And discrete variable is not necessarily integers, right? We could have 0, pi over 2, pi, 3 pi over 2, 2 pi, etc. And that would still be a valid discrete variable. The difference between them is when we look at a bounded range, there's a finite number of values for a discrete variable. Within bounded range, finite number of values, right? So if we were saying x was between 0 and 2 pi, there would be exactly 5 possible values. Or x is between pi and 2 pi, there's exactly 3 possible values for this x. For this x, if we said it was between 10 and 20, there would be exactly 11 possible values, right? Versus for this x, if we said it was between pi and 2 pi, there'd be infinitely many values because the infinite amount of decimal places, infinite amount of precision means that there's infinite possibilities. And then within discrete variables, there's the special case called binary variables. And so that's when there's only 2 possible values, like x exists 0, 1. So no matter what these mean in real life, we could have 0 represent one value and 1 represent the other value. For example, we could say x equals 1 if it's sunny outside and 0 if it's not sunny. And so x would represent whether it's sunny. And that this works out nicely using 0 or 1 values because we could do things like 100 times x. So now this is going to be 100 if it's sunny, and it would just be 0 if it's not sunny, right? For example, we could say you earn $100 when it's sunny outside. Let's say like you make $90 when sunny, 50 otherwise, 50 when it's not sunny, right? Then how much money do you make? That's, well, we have when f of 0 is going to be 50, f of 1 is going to be 90, right? So we want our f of x to be 40x plus 50. So you can see clearly this is just a simple function I came up with. When we plug in 1, we get 90. When we plug in 0, we get 50. Yeah, and we An important thing to note is that a discrete variable is equivalent to multiple binary variables. If we compare each pair of values separately, then it's a binary variable. And if we have enough binary variables, then it covers the entire discrete set. So like, let's look at an example. A discrete variable would be something like this. It's 0 if sunny, 1 if rainy, and then 2 if cloudy. So there's 3 possible values. It's not binary, but it is discrete because there's a finite number of values. And then x1 equals our old x, 1 if sunny, 0 otherwise, right? x2 equals 1 if rainy, 0 otherwise. x3 equals 1 if cloudy, 0 otherwise. So we've taken each of these values and turned them into their own discrete and binary variable. That's called one-hot encoding or binary encoding. Um, so yeah, really, binary is a subset of discrete, and discrete can always be converted to binary variables. And when we have something like this, expressing logic, um, like expressing we make $90 with sunny and 50 otherwise, in terms of this x, like that doesn't like make a lot of sense. Writing a function like that, that's not really possible. But with these binary x, now we can do the binary expressions that we were doing before, right? So let's say like you earn 90 if sunny, 50 if rainy, and then 60 if cloudy, right? So our expression for this could be 90x1 plus 50x2 plus 60x3. 90 times whether it's sunny, 50 times whether it's rainy, etc. And then in this case, right, exactly one of these variables would be 1 and the other two would be 0. So if they're being selected, then we have to add that as a constraint. If it's from a known data, like this variable is from a known data set, then you do the calculations and it's going to work out. Only one of, like x only takes on one value, so only one of those binary values is 1. But anyways, let's look at another example of an expression. Like let's say we make $90 unless it's raining, right? So we could do 90 times 1 minus x2, because this is going to be 90 when x2 is 0. When x2 is 1, it's going to come out to 0. So this is like the not operator saying when it's not rainy, we make $90. And we can also do the example $90 if not cloudy, not rainy. So that would be the same as $90 if sunny, but we could write the expression this way a little more complicated, right? So 90 when it's not cloudy or it's not rainy. Oh, not cloudy and not rainy. That's what I mean. They're together. So it's both not cloudy and not rainy. Then we make $90. So 90 times 1 minus x2 times 1 minus x3. That's the same as saying 90 minus 90x2 minus 90x3 plus 90x2 x3. And like that's going to be equivalent to 90x1 since, right, when x1 is 0, these guys are 0 and the whole expression is 90. When it's not 0, exactly one of those is non-zero, and so Yeah, if exactly one of those non-zero, it's like that. This would be like if it's possible for x2 to be 1 and x3 to be 1, we would want to make sure we have that added so that we're not double counting this minus 90. Um, yeah, like looking at binary expressions is a good thing to do next. Um, right, so I was multiplying for and, right? If we were doing or, we would want to add x1 plus x2 times 90. Then we would end up with 90 if it was sunny and x1 was 1, or if it was rainy and x2 was 1. And the other type of variable to talk about is random variables. This is a little bigger of a concept, so like I would defer to another video on it, but basically our x is no longer a deterministic variable. That means known and unchanging. Now x takes certain values with known probabilities. So we know the possible values for x, and we have um, the probabilities for those. Takes values with known probabilities. And then, so we've talked about optimization problem models, types of variables, right? We could easily write a data or decision model that uses binary variables and discrete variables and random variables. If we have random variables, then we call it a probabilistic model or stochastic model. Like there's certain probabilities, and we have to deal with variables that are not known to be unchanging, right? Let's go back to data models and introduce the two main types of data models in discrete learning. One is regression, right? So in regression, we're predicting one variable from other variables or as a function of other variables. For example, we have y, or just generally y equals x1, x2, dot, 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 xp. So I'm just saying whatever our input variables are called, like they could be about the weather or whatever, we're going to assign them variable names x1 to xp, and then y is the output that we're predicting, right? So y would be called the response, and x would be called the regressors. And before we already talked a linear model. So linear model ax plus b, now we have more than one. So we could do beta 1 x1 plus beta 2 x2 plus dot 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 plus beta p xp plus beta 0 for our constant term, right? We could also have some odd model for y, like y equals beta 2 x1 squared plus beta 1 x1 plus beta 0. That would be like quadratic plus linear. Or we could have something that's straight up quadratic, like beta 0 plus beta 1 x1 squared plus beta 2 x1 x2 plus beta 3 x2 squared. Um, but all of these are equivalent to linear model if we do transformations to the variables before plugging them in, right? So what I mean by that is, like, let's say we have x1, x2, and y. We know certain values for these, right? Well, then we could calculate another column for x1 squared, and we would just be taking each of those values and squaring them. For x1, x2, we would just be taking one of these values, one of these values, and multiplying them together. Um, yeah, and generally, when we're saying regression, y is a continuous variable. When we have discrete y, that's the other type of model, classification. So regression with discrete and finite y. So we don't have an infinite number of y values. Oh, well, going back to regression, not all regression is equivalent to linear models. We can't always do that, right? For example, if we did y equals log of beta times x, there's no way we could write it as some new beta times our old x, right? Or even our function of x, right? Before we were able to just apply some new functions and then do a linear coefficient. Now, this would not be able to be solved with linear regression. And of course, there's some functions that are way more complicated um, to handle much harder situations. Um, Anyways, back to classification. We've introduced that is actually just a subset of regression problems. Classification problems have um, discrete and finite y, so there's a certain number of values, and we call those y values classes, right? Y values are called classes. For example, we could have a data set like this. X1 is continuous, let's say, 1.2, 2.3, 1.4, 1.6. X2 could be binary, like 0001, and our Y could be binary as well, like 1101. So now we want to predict what, given an x1, x2, is Y going to be class 0 or class 1? So it's like we have two categories of data points. One category where y equals 1, so that could represent one group of points, and then y equals 0 represents another group of points. And as I mentioned in this regression, the y value is continuous, but the x value doesn't have to be continuous. We're just multiplying a coefficient to it. If it's discrete, then like our beta is not really accounting for the fact whether discrete x is discrete or continuous or binary or whatever. But it's still like we probably wouldn't want to do it with binary, because binary variables are often categorical. Like up here, we were saying each category has a different meaning. We don't want to plug that into linear regression. You do want to separate them out into 3 binary variables, then you can plug it into linear regression. But really, you should just watch um, my video on linear regression to understand more about what regression is. But classification is also important to understand from a high level. Like, given a scenario, you want to think, okay, I'm predicting the value of something. Am I predicting a categorical value, like red or blue, or am I predicting a numerical value, like liters? So in classification, right, we're saying y is a function of x1, x2, but we want the output to always be 0 or 1. So this function is going to be a little more complicated than a linear function. One example we could do is logistic regression. So logistic regression is a classification technique, right? So our y is now binary, right? And we have x1 and x2 are other variables that are not categorical, right? So instead of saying y equals a value, we're going to look at the probability y equals 1, the probability y equals 0, and then the maximum of them is our prediction, right? So I mean, we could denote that as y hat equals argmax over I equals 1 to probability y equals j. Let's use j instead of I because we were using I for the index, right? We can use I for the index, j for the classes. But anyways, in this model, we have a function for each of these. This one is going to be exp beta 0 plus beta 1 x1 plus beta 2 x2 over 1 plus exp beta 0 plus beta 1 x1 plus beta 2 x2. Probability y equals 0 equals 1 over 1 plus exp beta 0 plus beta 1 x1 plus beta 2 x2. And so both of these probabilities have to add up to 1. And we can see that in this model, it's guaranteed to do that because like when we add the two fractions, our numerator is the same as the denominator. Here, this is like the utility or weight of class 1, right? And then the denominator is normalizing it so that when we add utility of class 1 plus utility of class 2, that gives us the total utility, right? So it's like the weight of class 1 divided by the total weight gives us a probability for class 1. And thinking like, why is there a 1 here? Well, it's like we're doing exp of 0 because that equals 1. And then ultimately we would have to define an estimation technique like least squares, how we're going to get beta hat 0, right? So, and beta hat 1 and beta hat 2, right? We want to be able to write them as some equation, and you can do that using least squares, minimizing sum of squared error, or you could do maximum likelihood, where you're writing the likelihood of the parameters in terms of the data set and maximizing it. Right, depending on our model and our optimization problem, which would be the objective functions that chosen, we're not always going to have an optimal solution, but you should be able to approximate or find a locally optimal solution if it's a like problem of importance. And some estimators are biased where like the expected value is not the true parameter value, but those can be useful too. And so basically I've covered what an optimization problem is, what data and decision models are, what different types of variables are, and the regression and classification problems, which are two very common problems in machine learning. We're just given other variables, predict one variable. There's other problems like clustering, giving a data set. We want to decide which groups of points are similar to each other. That would be a data model and also a straightforward problem, right? But I encourage you to look into different regression techniques, classification techniques, and then more advanced data and decision models, what a random variable is. And then you're really on a good track to learn data science.